Hello everyone, welcome back to Labtube. In this video I'm going to do question 13 from section 16.7, which asks to evaluate the surface integral of the function z squared over the part of the paraboloid given by x equals to y squared plus z squared for x being between 0 and 1. So the first thing here to see or to know, to recall, is that first step to evaluate surface integral is to find a parameterization for that surface. So parameterize S, meaning that you have to find a vector function with two parameters u and v, such that if you let your parameters vary in the domain D, then you get the surface, the whole of your surface. If you have such parameterization, then the second step would be you have this surface integral. This is nothing but notation, but when you have that parameterization, then you can make it to a double integral. So that double integral would be in terms of u and v, your parameters. The region would be the region on which your parameter vary. Your function, instead of putting your x and y and z, you have to plug in your parameters into your function. And for ds, the integral element, you have to do this. You find ru, find rv, cross product them, it is a vector, and then find its length, multiply by du, dd. So if you do all those steps, you get a double integral, and then from there you know how to evaluate a double integral, make it penetrated integral, and do inner one, do outer one. Okay, this is the general, and now let's see what is the surface in our case and how we can parameterize it. Okay, the surface is paraboloid x equals to y squared plus z squared. So paraboloid of that form is like this, coming out of the board. So it's a ball looking outward, and then z is equal to 0 there, z is equal to 1 is here. Okay, so I have to find a parameterization for this. This is very much similar to the case when you have graph of a function, but with one difference, that this time your variables are y and z, and x is defined in terms of y and z. So basically what you can do, the parameterization, this time plug y and z to be your parameters. And then so I have to give three components, x, y, z, in terms of x, y, and z. So for first component, which is x, it is given by this. Second component, which is y, is equal to y. And the third component, which is z component, is given by z itself. So that is a parameterization. Okay? But what is the region on which if we change y and z, we will get the paraboloid of that part? So for that, you need to know that x equal to 0, it's going to be always x bigger than equal to 0. But for x equal to 1, if you intersect x equal to 1 with this, then your x and y plane find the shadow on xy plane, sorry, y and z plane, what you will find is a disk of radius. Okay, let's figure out that x is going to be less than equal to 1, but x is y squared plus z squared less than equal to 1. So this is x, yes? X is supposed to be less than equal to 1, so y squared plus z squared should be less than equal to 1. So this is a disk of radius 1. So that's the region. So D is all y and z such that y squared plus z squared is less than equal to. Okay, great. Now we found the parameterization, we find the region. Now we have to go and find this part, our u cross rv. For us, our u is partial derivative of your vector function with respect to first variables. With respect to y, it is equal to 2y, 1, 0. And with respect to z, the second variable is going to be 2z, 0, and 1. And then cross product. And cross product is going to be 1. 1 minus 0, and then 0 minus 2y, and 0 minus 2z. Okay, that's the vector ry cross rz, and its length is equal to 1 squared plus 2y squared, which is 4y squared, and plus 4z squared. Okay. So I have everything ready now to carry out this computation. Integral of z squared ds. All three steps. The region for u and v. For function, instead of variables of your function, try to plug in the parameters. Parameters here are y and z. There's no x there, so writing z squared in terms of y and z would be z squared itself. And then ds would be length of this guy, which is 1 plus 4y squared plus 4z squared. I don't need that. Times dy dz. Okay, great. Now everything is ready there. The only thing is that the region so this is a double integral, yes? I have to make it to an iterated integral, but to make it into an iterated integral, it would be easier to write my variables in polar coordinates. Here I don't have x and y, I have y and z, but I can apply the same things. So first variable, let first variable to be r cosine theta, and second variable to be r sine theta. Okay? Then my region, which is disk of radius 1, is given by theta starts from 0, goes to 2 pi. And r goes from 0 to the radius of that disk, which is equal to what? 0 to 1. Okay, that's good. Now for z, I have to plug in r sine theta, and for y, if I factor out 4 here, I'm going to have y squared plus z squared. Plug in polar coordinates for that. What you will find is r squared times sine squared plus cosine squared, which together gives us r squared, 4r squared. And dy dz, remember in polar coordinate, dx dy changes to r dr d theta. So r dr. So everything is ready to go. I have 0 to 1 of r cubed. Let me write it r squared sine squared theta 1 plus 4r squared r dr. This is an iterated integral, and I have to evaluate the inner integral first, then the outer one. How I can evaluate that inner integral? Now that's the question. Note that I have 1 plus 4r squared here, and its derivative is 8r. I have r here. If I divide by 8 and multiply by 8, I will get the derivative of this thing. And r squared also can be written in terms of 1 plus 4r squared. What I mean is use substitution. Set, not u, let me, t to be 1 plus 4r squared. Then in that case, dt is going to be 8r dr, and from that r dr is going to be 1 over 8 dt. And also, I can solve this for r squared and get r squared is equal to t minus 1 over 4. So that means the integral, I can take out the sine squared, and I can write r squared 1 plus 4r squared r dr is equal to, I can write everything in terms of t, so t minus 1 over 4, that's for r squared, over root t, r dr is 1 over 8 dt. Now we have we found the antiderivative of this function, but let's just plug in the boundaries for that. Boundaries would be for t, for r equal to 0. If r is 0, then I get t equals to 1. For r equals to 1, I get t equals to 1 plus 4 is 5. So I have boundaries 1 to 5, 1 to 5, and then this goes from 1 to 5. Okay, 1 to 5, plugging everything there, 1 over 32, 1 over 32 times plugging 5, it is 2 over 5, 5 to the power 5 over 2, minus 2 over 3, 5 to the power 3 over 3. Okay, that's the inner one, minus plugging 1 to the power, any power is 1, so I have 2 over 5 minus 2 over 3. Okay, and if you compute this thing, I already did this, so let me just write the answer for that part and then use and go ahead and compute the whole double integral. It is going to be 1 over 120 25 root 5 plus 1. So if you simplify this, this is the number you're going to get. That's great. Now what we have is that we have value for the inner integral. So it is equal to, I can erase this and then use that for, actually I can erase this part. That's good. Then I have integral 0, this constant comes out, so I can write 1 over 120, 25 root 5 plus 1. Then there's no r, the remaining part is 0 to 2 pi sine squared theta. Okay, that's just one regular integral, and to evaluate that kind of trigonometric integrals, we use the double angle formula for sine squared. Then you just find antiderivative of that, 120, 25 root 5 plus 1. And it is equal to, I have half theta here minus 1 over 4 sine 2 theta going from 0 to 2 pi. If I plug in 2 pi, this will be 0, and plug in 0, this will be 0. The only value I get from this whole thing is 2 pi over 2, which is pi. And the whole value of this integral, the total, is going to be this number times pi. Okay, so now very quick review of what we did. To evaluate surface integral, I need a parameterization. The parameterization in this case was given based on this equation. Parameters were y and z, and x is written by that. Then we found this value, and then change our surface integral to a double integral over the region for y and z, which is a disk of radius 1. Plug in everything in your function, write surface integral element, and then we got this double integral. To evaluate double integral, we changed it to an iterated integral by changing it to a polar coordinate, and then do inner one. We did inner one. There was some gymnastic we did there, and then outer one. Now that's the value we were looking for. And thank you for watching this video.